Okay, thanks everyone for coming. This is the first seminar of 2024, and we're very happy to have Bruno speaking to us today about some complicated and interesting number theory topics, I guess. Or,
Yeah.
yeah, so
So
yeah.
yeah, okay, yeah. So this is an adaptation of a talk I gave last December in New York. Uh, that talk lasted about I think 3 to 4 hours, so I had to cut out quite a bit of things. Originally, it was planned to be even longer, but it was sort of cut short. So the ideas that we'll be developing here were developed. So the title is, of course, Iwasawa theory. But what actually is Iwasawa theory? So the the these are sort of cyclotomic methods um, developed by Kenkichi Iwasawa um, in the late 50s. Iwasawa uh, developed in the late 50s in order to answer some fundamental questions that were still left unanswered about an object known as the class number of a number field. I'll explain all those concepts in a second. But what exactly was being studied was what are the divisibility properties of this number. So specifically, what was discovered is that for certain towers of field extensions, so specifically for field extensions that look like this, K2, all the way up to some K infinity, where we also have that the Galois group of K infinity over K is isomorphic to the p-adic integers. For these so-called p-adic extensions, it was found that the class number of these sort of intermediate fields have a nice pattern. And specifically what was found is that you can find the exact order of whatever prime number is dividing this class number, essentially. So you can there's a nice pattern for this alpha. And here, to repeat, this is like the maximal power of p that divides the class number. So to get started, first of all, we have some historical results about how this class number works and what it even is. So first, to define some concepts, we say that k over q is a number field if k is a finite extension of the rationals. So this is a huge class of fields, and we still don't know a lot about many of them. And we'll see that at some point in this talk, we'll actually restrict our attention to a certain subset of these number fields that include something called the cyclotomic fields, and those are going to be the ones that are of the most interest to us, essentially. So we have this number field, but now we also need to define the main number, or sorry, constant, let's say, of interest, namely what the class number is. So what is h of k? So the idea is that you take so you have inside Q you have the integers. So we have this number field extension. Then we have something called the ring of integers. And you can imagine that the ring of integers is essentially what z is to q, then the ring of integers is that sort of to k. Specifically, these two are related by the fact that O of k is the integral closure of z inside k. So this means that we essentially take all the polynomials. We take all the polynomials with coefficients in z, and O of k are essentially all the solutions to all those polynomials that live inside of k. Okay, so
Just a
yeah.
silly question. Can you just give a concrete example then of like a minimal example of a K and the O
Oh
of
yeah,
K?
of course. So an example of a number field would be, for example, q adjoin the square root of 3 over
Perfect.
q. So there's a general class of these as well. Whenever
Mhm.
d is a square free integer, so it has no factor that's a square. This actually forms a number field, and these are called the um, quadratic extensions. The
Right.
real quadratic extensions.
And then the O of K would be like
So this is quite an interesting for quadratic fields. We have quite an interesting description. So O of k is equal to, we have two cases. So if it's equal to z adjoin the square root of 3, or sorry, the square root of d, when d is congruent to 3 or to 2 or 3 mod 4, and it's equal to z adjoin 1 plus the square root of d over 2 when d is congruent to 1 mod 4. It's a bit non-trivial to actually go and see this, but I think I'm not going to go into too many details about this specific calculation, but always I think it's possible to always algorithmically determine O of k in some like nice time complexity, though my knowledge of number theoretic algorithms is quite minimal, though that's quite big field in of itself. But here we're going to be talking much more from the sort of theoretical side of things than from actually being practical. Okay, so to start off, so now that we've defined O of k, we can finally define what the class number is and why it's interesting. So the class number is one of the biggest sort of mysteries in number theory. Calculating it is essentially near impossible algorithmically. All the algorithms have some god awful time complexity to them, and essentially finding a good way to calculate it is one of the biggest, let's say, open problems in number theory. So let's actually define it. So the first thing we do is that we define what is known as the class group of k, or of O of k, essentially. What this is you can show that all the ideals in O, so we'll call all the ideals in OJ. So this is the group of ideals of O of k. So this is a group under like ideal multiplication. So if you remember, I multiplied by j is the set of all finite linear combinations of like elements of I and j combined by one another. So plus a2 b2 plus dot 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 plus an bn, where ai's are in I and the bi's are in j. Okay. And this is a new ideal. So we can actually sort of show that within O of k, these sort of ideals form a group under this operation. defining the inverse and such is a bit difficult and off topic. So let's just black box this sort of information that these form a group, since it won't play a big role in what's about to come. But when we quotient it out by the subgroup of all principal ideals in O of K, we get this quotient group that's called the class group of K. So this is called a class group. And its cardinality is called a class number. So H of K is defined as the cardinality of CL of K. And it's a sort of well-known number theory fact that this number is always finite. If you want some sort of keywords to describe why we have this nice structure on J, you can say that it's because O of K is something called a Dedekind domain, and that has some nice properties that allow us to sort of show that the J's form a group. And what we'll actually show, and sorry, we won't show this, but it's known that within Dedekind domains, so specifically within O of K, the ideals actually can be uniquely factorized into prime ideals. So we have unique ideal factorization. So this is essentially the equivalent of how we have unique factorization into prime numbers in Z. In these general O of Ks, we don't have unique factorization of elements, but we do have unique factorization of ideals into prime ideals. So any ideal of O of K can be uniquely written as a product of prime ideals, not necessarily unique. Okay, and the theory of how prime ideals work in number theory is quite deep, and I'll be mentioning some theory later on, but I'll introduce everything when the time comes. Okay, so to start off, something that I want to showcase is the following. So historically, so I'm going to be approaching this from a somewhat historical perspective on how all of these ideas were slowly developed over time. So specifically to start, we'll have to combine two very old number theoretic concepts. To start, we'll define Dirichlet characters. And then using them, we'll define L functions. L functions. We will show that L functions actually contain information about H of K. Then, since maybe finding out the entire number is a bit too difficult, we might consider dropping down a level and asking, okay, by which prime numbers is H of K divisible? So we will, to find this out, we'll have to talk about p-adic L functions. And then after that, this is the point at which Iwasawa came in. And after that is what's, I'd say, generally considered as like Iwasawa theory, because he did some very specific things that, as we'll see. Okay, so to start off, let's quickly define what Dirichlet characters are and quickly how they work. So Dirichlet characters are essentially multiplicative maps. So a Dirichlet character chi is a multiplicative map from Z mod NZ, the units of Z mod NZ, into the multiplicative complex numbers. So specifically, what we'll be talking about are primitive Dirichlet characters. So what I mean is that when M divides N, we have a natural map of Z over NZ into Z over MZ. And this gets us a little nice diagram. So here we have chi, which maps the units of z over nz into into the complex into the multiplicative complex numbers. Then we have this sort of natural map into z over mz, and question is, when does this exist? So when does a map that essentially when does chi factor through z over mz? Well, this needn't hold in general, and specifically when it holds, the minimal m for which it holds is called the conductor of chi is the minimal m for which this map factors. And this is important simply because taking the conductor, taking the primitive character, so that means instead of considering a character going from z over mz, we just consider chi as this map here. So the chi is called primitive when chi is called primitive when n is equal to conductor. So chi is primitive. Okay, so a quick example is, let's consider a chi. I'm going a bit fast just because there's a lot to cover, but I'll give an example and it'll be a lot clearer when I sort of give this example. So consider a map chi from the integers modulo z, specifically the units of the integers modulo z, into the multiplicative complex numbers, and it's defined as follows. So we have chi of 1 is equal to 1, chi of 3 is equal to -1, chi of 5 is equal to 1, and then chi of 7 is equal to -1. Okay, so clearly you can sort of see that we have a bit of redundancy here. Namely, chi of n plus 4 is equal to chi. So it is equal to chi of n. So we might as well sort of consider chi, instead of being a sort of character modulo 8, we might as well consider it character a character modulo 4. Sorry. And another way to see this actually is a sort of Galois theoretic perspective. So so say we have the following. Sorry. So okay, so sorry, I'm getting a bit fast-tracked here. So this is the idea of a conductor. It's sort of the minimal n that eliminates as much redundancy in the sort of character as possible. So instead of considering this as a character mod 8, we might as well just consider it a character mod 4, and that works just as well. So another way to see this that's a bit more, let's say, algebraic and a bit more sort of maybe useful to some is to note the fact that for the extension Q adjoin the nth root of unity, we have that the Galois group of this extension over Q is equal to, is isomorphic to the units of z modulo nz. So instead of considering chi as a character on the on the integers modulo n, or the units of the integers modulo n, we can consider them as it is a character on the Galois group. So we can sort of find the conductor more easily via essentially the following via essentially the following methodology. So sorry. So what's essentially the kernel of this map? Well, we have that the kernel of chi is 1 mod 8 and 1 mod 8 and what did I say, 5 mod 8. So this is essentially the same thing as as chi is equal to equal to the Galois group of Q adjoin the eighth root of unity over Q adjoin the fourth root of unity. The reason for this is that we're looking for a subgroup of order 2, and it can be shown that this is the sort of only subgroup of order 2 in this Galois group. So sorry. So essentially just quotienting out by this, we get that so quotienting out by quotienting out the Galois group Q adjoin the eighth root of unity by over Q over the kernel of chi. We have that essentially this is just a character on the Galois group of Q adjoin the fourth root of unity over Q. Okay. And this essentially automatically just spat out whatever the conductor was, right? We have that our conductor in this case is 4. Okay, so oh my god, it's already been half an hour and I'm not even started. Okay, so so the idea here is just that these clearly contain some sort of algebraic information about these sort of Galois extensions of cyclotomic fields. And what can actually be shown is that these contain much more than that. These contain something called it can be shown that chi contains information about something called the ramification of primes. And the sort of idea of the ramification, what ramification means is that it's the study of how ideals essentially factor into primes, right? So so it can be shown that chi in a very specific way will get you the sort of indices of the factorization of some ideal into like prime ideals. And I'm not gonna go into that here because I don't have time, but that's sort of gonna be the key ingredient to why we want to consider these. These contain a lot of algebraic information that's very useful to us. So so how might we study these more easily? Well, studying them always algebraically is a bit hard. So what mathematicians sort of did was that they said, okay, well, these contain algebra. These chi's, they contain a lot of algebraic information we're interested in. But what we noticed is that if we input them into a very specific infinite series, this infinite series has amazing analytic properties. So why not use those amazing analytic properties to allow us to study these algebraic properties in sort of more depth? And that's the motivation essentially for how L functions are used. So an L function, or is here specifically I'm talking about Dirichlet L functions. A Dirichlet L function is an infinite series that inputs a sort of complex number S and this number chi, or sorry, this character, this Dirichlet character chi, and it's defined as being the infinite series from n equals 1 up to infinity of chi of n divided by n to the s. Okay. So okay. So now what specific information does L contain that makes it useful to us? Well, here I have a very long-winded proof of how L contains a lot of information we're interested in. But very quickly, the idea is that L can be used to find a very nice formula for something called the relative class number, as we'll see in a second. So, okay, let me just sift through my papers here because I'm skipping past half of the stuff. Okay, here we go. So, firstly, I want to talk about one thing before we sort of continue, just so I'm up to date with all the definitions. So let's define what a C. So here's the idea. So it was discovered at some point that there's a very specific class of number fields that have a very unique properties. Namely, there are these fields called CM fields, and we'll see in a second that they're super useful. So CM fields have the following property. So if essentially, okay, sorry. So CM fields consist of two parts. So firstly, you have a field called K plus that's totally real. So what that means is that all the injections of, or sorry, all the inclusions of K plus into C, their image is contained in R. Okay, and over that, what we have is K. So this is some overfield over K plus, and the thing is that K is totally imaginary. So it's the complete opposite of sort of K plus. Namely, K is the K is K over K plus is a quadratic extension. So that just means a field extension of degree 2, and K is totally imaginary. So it's just the opposite of this statement. So all the images are not contained in R. Totally imaginary. Okay. So why are these useful? Well, these are useful because a lot of number fields that we might be interested in are CM. Specifically, the number fields Q adjoin the nth root of unity, these are all CM. And their totally real subfields are Q adjoin zeta n plus zeta n to the minus first. This is the K plus from this definition. Okay, so what's the property that makes them useful, essentially? Well, the property that makes them useful is the fact that the class number of this K plus actually divides the class number of K. And this is great because this lets us sort of consider less information at once. So specifically what I mean is that for example, in the in these cyclotomic fields, we might define, so we actually do define this, we define the relative class number H minus as being H of K divided by H of K plus. So this is called the relative class number, and the idea, or the big idea, is that L functions can be used to give a very nice formula for this H minus, and I'm going to give it now without the proof, since the proof would be sort of long and it would require introducing a million more concepts that we don't have time for right now. So specifically what L functions show us they show us that H minus of K for some CM field K is equal to QW times the product over all odd chi of something called minus 1/2 times, these are called the generalized Bernoulli numbers, and I'll explain everything in a second. Okay, so first things first, let's sort of define what everything is here. W is the number of roots of unity contained in K. Q is it's a very specific number, but it's essentially okay. So what the sorry, I misplaced all my papers. I just want to be sure I'm giving the right definition. Okay, so Q is defined as the index of a certain subgroup of the unit group. So here's essentially the idea for how to think about Q. So we have sort of O of K and we have O of K plus. Now, there are some units inside here, and we'll call those units E, and we'll call the units inside O of K plus E plus. And as well, let's say that capital W, this is the group of roots of unity. Sorry, the roots of unity in okay. So since remember K plus is totally real, so it can't contain any roots of unity apart from 1 and -1. Otherwise it would have to be at least partially imaginary. Okay, so Q is defined as the index of E with the subgroup W multiplied by E plus. And this is always known to be either 1 or 2. So either the units of the sort of overfield are just the units of this totally real field multiplied by all the roots of unity, or there's like a double stacking sort of effect for these two that like two copies of these sort of roots of unity multiplied by the real units are just stacked on top of each other. So Q is always known to be either 1 or 2. And finally, we have these generalized Bernoulli numbers, and these are the ugliest things sort of that exist. But they're essentially defined as a certain, using a, excuse me, using a certain function. Namely, we'll do essentially an analogy to how the usual Bernoulli numbers are defined. So the usual Bernoulli numbers are defined via the fact that the function t over e to the t minus 1 can be defined as an infinite series starting at n equals 0 up to infinity of the Bernoulli numbers multiplied by t to the n over n factorial. And we sort of generalize this to the case of characters, and we say the following. So the function sigma a equals 1 over f, this is the conductor of this is the conductor of some Dirichlet character chi. The function defined by chi of a times t e to the at all divided by e to the ft minus 1 can be written as an infinite sum starting at n equals 0 up to infinity of these generalized Bernoulli numbers with respect to some specific character we chose chi times t to the n over n factorial. Okay, and there are a lot of explicit ways to sort of define these Bernoulli numbers in other ways, and specifically there are a lot of different values of the L functions that are associated to these Bernoulli numbers. So as an example, for n greater or equal to 1 a natural number, we have that an L function of 1 minus evaluated at 1 minus n with respect to some Dirichlet character chi is actually minus Bn chi, so the nth generalized Bernoulli number with respect to chi divided by n. So we know a lot about the integer values of about the negative integer values of L functions, but we barely know anything about the positive sort of integer values of L functions. So this is about as best as we can get to sort of evaluating what we currently know. Okay, so so this is the point we're at, and this is already quite a lot. The fact that we even have this formula is incredible to us, just because everything in this formula is easy to compute sort of via a computer. So everything here is very doable, and we don't have any problems with sort of having to find some super complicated algorithms for anything or whatever. This is very well known, and it already gives us one half of the equation towards finding whatever is hidden inside the regular class number if we already know its relative class number. So the next piece of the puzzle would be sort of finding out what this class number of the totally real field is, and we'll talk about that a bit more a bit later on in this talk, because that's quite a sort of deep dive in of itself into certain groups of units and things, as we'll see. Okay, so after this, we this point that I'll mark by a star sort of tells us that L functions have a lot of power to them, since this formula is actually proven to a big use of just like sort of L function values. So if L functions hide so much information about the class number, how can we essentially find out more? So the next natural step would be, instead of maybe trying to find as much information about the full relative class number, let's, sorry, I actually skipped a section. Before we go on to finding what the divisibility properties of this number are, I want to take a short tangent to mention an interesting result. So we actually know how this number acts asymptotically. So then this was actually discovered quite quite long ago. Specifically, we know that the logarithm of h minus of, let me establish some notation to make things easier. We'll call h minus n the relative class number of q adjoin the nth root of unity. So specifically, what is known is that asymptotically, the logarithm of hn minus sort of grows similarly to 1/4 of the sort of Euler-Toscan function of n multiplied by the logarithm of n itself. So specifically, what does this tell us? Well, since we know that this grows to infinity as n grows to infinity, we can see that for large sort of n, we have that that hn minus is also quite large. And I think it was early on in the history of number theory, it was quite a problem sort of finding out specifically how hn grows. And this answered a big problem, namely, this sort of taught us that hn can grow to sort of as large values as we essentially want it to be. I think very early on, this is like 19th century number theory. There was, I think, a problem was whether or not hn minus or h minus is always like bounded, or I think something like that. And this sort of theorem proved that it wasn't. But to actually prove this result, it requires a much more difficult theorem called the Brouwer-Segal theorem. They call the Brouwer-Segal theorem that I'm not gonna even start going into right now, and that establishes certain asymptotic behaviors of the class number itself, but that's infinitely sort of harder to prove than using the Brouwer-Segal theorem to prove this result about the asymptotic behavior of the relative class number. Okay, so now the final step in our evolution up to sort of talking about all these things is asking the following questions. So what tool can we use to find out the what tools can we use to find out what, like, maybe the p-divisibility properties of this number are? So when I say p-divisibility, I mean which prime numbers divide these relative class numbers. And a natural step in towards finding that out is defining essentially the p-adic variant, analog of the regular Dirichlet L functions. Because if the Dirichlet L function itself tells us the full sort of relative class number, then maybe the p-adic sort of L functions can tell us how the p-divisibility properties of this, since the p-adic numbers essentially give us the p-divisibility properties of any integer we want. That's kind of like the point of the p-adics anyway. So there are a lot of ways to define the sort of p-adic the p-adic L function, and there are two primary ways. The first one is using an explicit infinite series that's quite ugly and that doesn't tell us a lot. But the second way is using something called the Iwasawa constructions. The Iwasawa construction. And this will actually immediately give us a big result that we'll find sort of very useful. So what exactly is the Iwasawa sort of construction? Well, so this is just sort of to get into it, it is not going to be even at all trivial, but let's at least try. So here's essentially the, I'd say, shortened version of things. So at some point during the last, I don't know, 50 years or so. Oh, I didn't mention this. Ah, shit. Okay. Should I go back to this? Should I talk about the Iwasawa construction first? Okay. It might be useful to sort of introduce these concepts. Okay. So here's how the Iwasawa construction came about. So p-adic L functions were defined at that point. But they weren't used for anything really useful. What Iwasawa discovered, though, is very interesting. So there's a theorem of Iwasawa's that essentially says the following. So where's the correct paper? Where's the sorry, there are a million papers everywhere and I'm trying to find everything just so I'm on top of everything. So
no problem.
Here are two facts essentially that are useful. So there's a theorem of a guy called Stickelberger. What Stickelberger said is that there exists a certain ideal of the group ring of G. Here, there's so much to talk about. Here, G is defined as the Galois group of some abelian finite extension of the rationals. So this is abelian and finite. Of the rationals, and that has the following property. It it does something called it annihilates the class group. The class group. So what does this mean explicitly? Well, the idea is if you take any element of this ideal, the ideal I'll denote it by I, and it's called the Stickelberger ideal. So the Stickelberger ideal essentially does the following. Say you have some element, what should I call it? I don't know, sigma inside of I. And what it does is that there's a natural action of this sigma on the sort of elements of the, there's a natural action of this sigma on the elements of the ring of integers of this sort of number field. So we have, so if A is an ideal of O of M, then sigma acting on O of M turns it into some principal ideal. So this becomes some principal ideal. I.e., when you quotient out by the principal ideals, essentially, sigma inherits a sort of natural action. Excuse me. Sigma inherits a natural action on this quotient group, and that just means that whichever element of sigma you act any element of this quotient group by, you'll always get the identity element, i.e. just the sort of coset of principal ideals. And on first glance, this does not tell us anything. This looks as if it's totally, essentially, fucking useless. But it's not, in fact. It's incredibly useful because a following theorem of Iwasawa says that this ideal has an incredible property. So specifically, if we define R minus as all the so if we say R is Z G, I'm just trying to keep up with the notation I have on my paper. So I is the Stickelberger ideal. If we define R minus as the set of all elements in R, such that complex conjugation of this element gives us minus X, then we can also define I minus as I intersect R minus. What Iwasawa discovered specifically is that excuse me. What Iwasawa discovered is that the quotient is that the index of I minus and R minus is actually equal to the relative class number of whatever extension you're sort of looking at. And this was a sort of huge thing because it essentially gave us a way. It essentially gave us a way to connect L functions and the Stickelberger ideals. And then what Iwasawa did is he used the Stickelberger ideal as a way to construct p-adic L functions, as we'll see in a second. And this will give us a huge theorem on the structure of these relative. Sorry, I've been talking for a bit without drinking any water, so my throat is a bit dry. Okay, so before moving forwards, let's quickly mention Fermat's theorem. This is called the first case of FLT. There are two cases in classical cyclotomic theory. So Wiles used a completely different approach to regular cyclotomic theory when he actually proved FLT, but this was the historically main way that people thought that this Fermat's theorem could be approached. So what does the theorem actually tell us? So before starting the theorem, as usual, we have to define something new. We call I of p the index of irregularity of a prime number. And essentially, this has an absolutely sort of absurd definition, but the index of irregularity, if I recall correctly, is where's my copy? Okay, yeah. So the index of irregularity is a number that tells us how far from being a regular how far from being a regular prime number p is, specifically in the sense that a regular prime is a prime that doesn't. Okay, yeah, sorry. So it essentially, here's the idea. We have the Bernoulli numbers, right? Now, if p divides the numerator of any sort of bn, where n is an odd integer, an odd integer less than or equal to p minus 3, then p is called irregular. And specifically, and then that means that it's regular if p never divides any such numerator of a Bernoulli number. So so the index of irregularity is essentially the number of these Bernoulli numbers that are congruent to 0 mod p. And what does the first case of FLT say? Well, the first case of FLT says that if this index of irregularity grows more slowly than the square root of p minus 2, then FLT holds. So this is quite a powerful sort of sorry. Then the first case, of FLT holds. Specifically, the first case means that we have an equation x to the p plus y to the p equals z to the p, where sort of x times y times z, comma p is 1. The GCD of x, y, and z multiply all together, and p is equal to 1. So they're relatively prime. The second case is when this GCD is equal to p itself, and that's a far more sort of complicated case to essentially handle, and it has sort of more complicated conditions for when it actually holds. But using these sort of cyclotomic methods, so these means just like methods associated to the cyclotomic fields, we've managed to reduce FLT to essentially three conditions, and this is essentially one of them. I'm not sure if this was ever actually shown to hold. I'm not sure what the status on this is, but at least when the book I read was published, this was still unsolved. So I don't know if there have been any leaps and bounds in sort of understanding the index of irregularity in order to say, okay, it's always bounded by this sort of other function. Now, okay, so moving forward, we mentioned these Stickelberger elements, and going into the construction would be very time consuming, and I've already essentially wasted the hour I was given. So I'm just gonna be very sort of quick about everything. So the idea is that the idea is that the Stickelberger ideal has associated to it something things called the Stickelberger sort of characters, And using those, we can show the existence of three very special sort of series. So specifically what we're interested in is that we have series called F, G, and H that are inside a certain ring. The series ring of a certain ring. I'm not gonna go into how we actually define R here, since it's involved in of itself, and I'm trying to rush my best through everything. But essentially, we have that the p-adic L function then as chi can then be defined as follows. So it can be defined as this series. This series evaluated at so how does this go? Yeah, okay, of course. So then we have there's so much to talk about and not enough time. I'm sorry if it's a bit disconnected. I'm trying my best to sort of compactify everything as much as possible. So the idea is that okay, I'm not gonna write it explicitly, but the idea is these connect together to construct LP. So LP of S comma chi. So this being the p-adic L function. The way specified would have to go into what actually these Stickelberger characters are, and this involves factorization of Dirichlet characters and stuff, so I'm not going to go into that right now. But what does this give us? Well, this gives us a huge theorem that's sort of the main not the main point, but it's a way towards the main idea that or sorry, the main theorem, as I like to call it, of Iwasawa theory. Specifically, let's okay, yes, sorry. So yeah, sorry. So just give me a second. I'm all over the place right now. I just want to know that I got this right, because I know I made a mistake somewhere in this part, and I just want to make sure that I corrected it correctly. So as I recall, oh, okay, yeah, I don't think that's necessary here, but sorry, oh yeah, of course, I'm being a sort of a dumbass. Okay, so the idea is that all right, so the idea in essence is as follows. So sorry. So if we have, as I said before, some extension of like fields, so this is some k2 ... all the way up to k infinity. The idea is that if k infinity over what is it, over k0 has a Galois group isomorphic to the p-adic integers, then we have the following incredible fact. So here's how it goes. Let p to the e to the minus n be the exact power of p dividing h minus of kn. Then e to the minus n has the following form. So it's some constant lambda multiplied by n plus mu to the pn plus nu, where mu comma lambda comma nu are all independent of n. So the idea is, if you can calculate mu lambda and nu, for k0, you can extrapolate it using this formula for any n in this like sort of tower of field extensions, and then we can immediately know what power of p exactly divides exactly divides the elements in our sort of tower of fields. Now here we have a more, so this is a very famous theorem of Iwasawa's. I think I'd call it the weak Iwasawa theorem, because the strong Iwasawa theorem actually says that not only does E minus have this form, but if p to the En is the exact power of p dividing h of Kn, then e to the n also has this sort of identical form to it. Now, here we have a more sort of complex theorem. This is a theorem of sort of Washington and Ferrero. And it says that if if K over Q is an abelian extension, then mu is equal to 0. And mu here being this sort of constant we had in the theorem. So proving the Washington-Ferrero theorem is incredibly difficult. It's the most non-trivial thing you'd probably read in a single day, but it's incredibly powerful. It essentially says that in the tower of fields, for abelian extensions, instead of having sort of growth of h minus that goes like p to the n, it's actually reduced to just p to the n, like exponential growth, not super exponential growth, so that we don't have to deal with incredibly huge, essentially, numbers when doing these calculations numerically. Okay, so now, this theorem of Iwasawa's has given us a lot of information about H minus, but as I said earlier, or hinted at earlier, where is specifically is H plus hiding, and how does it let us sort of learn more about the full the full sort of theorem of Iwasawa's? Now, since it's already been an hour and I have stuff to do, I'm gonna cut all of this very short, and I'm probably assume that all of you are sort of aching for this to finish already. So at this point of the talk, I sort of, the methods become complicated enough that I think that actually mentioning anything would be sort of a hindrance to the talk itself, unless I had like 5 or 6 hours to like go into everything in depth. But sort of in short, here's how I sort of summarize everything. So the primary idea of everything going after this point is that Iwasawa theory doesn't deal just with these kinds of like field tower extensions. It deals with things that are far more general. Namely, it deals with something called lambda modules. So a lambda module is a module over the ring lambda, where lambda is defined as the series ring with sort of coefficients in the p-adic integers, lambda. And there are a lot of very famous results that Iwasawa discovered about these lambda modules. There's a theorem of Serre's that actually sort of tells us what the structure of these modules are like. So just the fact that we have a sort of structure theorem for these modules already tells us how much we kind of know about them. But the whole point is that using this huge kind of theory of lambda modules that I very much don't have time to get into right now, Iwasawa proved the main theorem of sort of Iwasawa theory. Namely, that if k infinity over k is a ZP extension, so as I said earlier, that means that the Galois group of k infinity over k is isomorphic to the p-adic integers. Extension is a ZP extension, then then e to the n is equal to lambda n plus mu Pn plus nu. The full Washington-Farrow theorem actually tells us that even for this full En, mu is still zero in abelian extensions. So the Washington-Farrow theorem is truly huge. But an interesting point I want to make before I sort of finish this off, sort of semi semi abruptly, is that before going into sort of FLT, a lot of the work that inspired FLT was actually done in exactly Iwasawa theory. And a lot of Iwasawa theory results actually talk about, actually were used in the proof of FLT itself. So, sorry. So specifically, Wiles and Maser proved, I don't know when this was, something called the main conjecture of Iwasawa theory. And the main conjecture of Iwasawa theory was concerned with talking about what these series actually look like, because not a lot was known about them. The way they're constructed is essentially you construct a set of very specific polynomials and then just sort of say we take the sort of limiting procedure as n goes to infinity of these different polynomials, but a lot of information is hidden behind that limit, and the main conjecture said some pretty complicated things about what the structure of these series looked like. And Wiles and Mazur proved them using a lot of the same machinery that later got used in the proof of Fermat's theorem. So essentially, after sort of the point where it cut us off semi-abruptly, a lot of the tools that become used are stuff like sort of modular forms and group schemes and who knows, and a lot of other very complicated machinery that would take us a whole semester to essentially get through. So that's why I had to unfortunately cut the bit short, because I don't think any of us have time to go into a full course dedicated to what the full power of Iwasawa theory actually sort of has behind it. So at the end of the day, I'd say that as I sort of said when I gave this talk in New York, I think that this talk turns out to be more of a sort of gentle invitation towards Iwasawa theory than actually sort of talking about what the full extent of Iwasawa theory hides behind it, because that's a topic that's too sort of broad to actually sort of get into right now. But okay, I think that that's sort of the point where I finish the talk, because I think I have to sort of get going now. But if anybody has any questions, I still have a bit of sort of time to answer them.
Okay. Well, thank you for speaking. I see two people had to dip right the last minute, but yeah. I actually have a silly question, and
Yeah, no, it's
since
okay.
I'm in charge, I'm going to take over. And so around halfway through, I was going
Yeah.
to ask, but you were on a roll.
Oh
Is
yeah,
that
sorry.
no. It's like, you know, at some point you said people historically were trying to compute these p-adic L functions,
Yeah.
right? But the p-adic L functions look like they're defined. So you defined
So,
these L functions for me
yeah,
for Dirichlet characters.
okay, so this is maybe a good point to sort of point out. So um the concept of what a p-adic L function doesn't sort of sorry, this is kind of hard to explain, but in like full general, so I don't know at what point sort of these p-adic L functions were actually defined, but they were defined using a sort of so the procedure that was used wasn't anything super like technical. It's just sort of hard to explain the exact motivation behind it. But sort of in number theory, there exists this sort of idea that for objects that exist for the rational numbers, you can, in a sense, push them to be to have analogies in the that like take the for example p-adic rationals as inputs. Now this is a very informal procedure essentially, and this is sort of the idea of what was done to define these p-adic L functions early on. So the idea was sort of okay, let me actually remember how this sort of went. So so they defined a sort of excuse me. So when I read it at first, I was like, what the hell is going on here? But the idea was, firstly, you define a sort of associated series to the original L functions. Then you argue via some arguments that I personally find like sort of weird, that this associated series can be in a naturally way sort of used to construct another series that we call like the p-adic analog of this series, and then using that associated series you go the other way around and say, okay, now that we have this like p-adic associated series, we can use it to define the p-adic L function. And if you want specifically, so in full, the p-adic L function actually has a series expression if you go via this method, and it looks something like, so LP of S comma chi is equal to, okay, so this is where it sort of gets intense. So 1 over F, where F is the conductor of this Dirichlet character, times 1 over S minus 1 times the finite sum as A from A equals 1 to F, where P cannot divide A, of chi of A times an object that I'll call brackets A. I'm not going to go into what this object is right now, times the infinite series from J equals 0 up to infinity of 1 minus S choose J times something called the Bernoulli polynomial of a specific thing. So so this is a very complicated expression, and it's sort of constructed using this sort of analogy idea that I mentioned earlier. So what Iwasawa did specifically is that he said, okay, so I've discovered that you can use another way to get this exact same expression sort of out of the Stickelberger elements that he was sort of working with at the time. So maybe it would be useful to give a reference to all the things I talked about. So this entire talk was inspired by a book of Washington's. This is the same Washington who proved the Washington-Ferrero theorem. So a book of Washington called Introduction to Cyclotomic Fields. And be wary, because it's very much not an introduction. It requires a solid grasping in algebraic number theory to sort of be able to read it. So I don't like the sort of choice he chose for the title, but that's whatever. This one goes, this book goes in depth on everything I talked about here, including all the theorems I mentioned, absolutely every single theorem I mentioned, Washington goes out and proves them in this book. So if you're interested in reading more and you have a grasp on algebraic number theory, this is the book to sort of learn Iwasawa theory from.
Right. I see. Okay, and that essentially answers my question too about the defined versus calculate thing. So, okay. Dalton, I don't know if you had any questions, or maybe this is all in Dalton's head already.
No, I saw this talk in New York already, so I don't have any questions.
Oh, okay. Okay. Um, okay. Well, yeah, I'm out of kind of my dumb questions. I have to admit the whole time I was kind of just imagining uh I was just imagining generalized Riemann zeta function.
Yeah, that's
Or at least so
literally what it is essentially.
yeah, exactly. So that was kind of what I was grasping to. That and the quadratic integers example or the Gaussian integers or whatever they're called. So
Yeah, the
um
quadratic example.
yeah, yes. So okay, thank
Okay,
you very
okay.
much, Bruno. We all really appreciate it.
Okay. No worries.
Yes.
This is the second time I've given this talk, so I've sort of I've gotten I don't know if I've gotten used to it, but sort of I enjoy talking about this topic, so
Yeah. Okay. Thanks very much.
okay.
See y'all in
No
the future,
worries.
I guess.
Okay, yeah, see you.